There we go. So I guess I'll write it. Oh, I don't have that on. Let's see. Can you see now? All right. Yeah, there we go. Let me just find some blank white paper. All right. So a couple things. Exam 1. That's coming up Thursday. Next Thursday, a week from today. So that will be the 12th. Should be the date that is specified in your syllabus and on Canvas. It's going to cover sections 1.1 through 1.7. So all of the chapter 1 material will be on exam 1. All of this formal logic stuff that we've been doing. So that's going to be on that exam. We're going to start chapter 2 today, or I expect to, but we won't get through, even a full section of that, so that won't be on the exam next week. All right. So are there any questions then before we jump into today's lecture? All right. So we started laying some groundwork last time of terminology for mathematical proof. And basically everything that we do in mathematics has to be proven. It needs to have some logical chain of reasoning that takes us from our axioms, the basic building blocks that we assume to be true, and build us and logically reason from those to any mathematical statement that we make. Okay, and so that's how we're kind of getting the beginnings of that in this class. Okay, but what we're going to see here is the sort of thing that every mathematician, or every good mathematician throughout history has done. Right? You go back to the beginnings of math. You go back to Euclid. He's proving everything rigorously through logical reasoning. Okay? So we said last time we're looking at theorems. Theorems are things that we can show to be true. And most theorems are stated in the form, if P, then Q. If some set of conditions are true, then some conclusion follows. Okay? And even a lot of theorems will also be written in the form, for every x, P of x. Right? So for every x in the domain, some statement is true. But we'll usually restate that. We'll treat that as saying, if x is in the domain, then P of x is true. Okay? When we're trying to prove this. All right, because a theorem can be thought of as a conditional statement. If the conditions are false, then the theorem is going to be true. But that's not an interesting case, right? We don't really care about something that's true because the premise was false. So we're going to just go ahead and assume, right? When we're doing a proof, we're going to assume that the hypotheses are true. Okay? We're going to go ahead and assume that. All right, so now, and we made some definitions for even. Even number is an integer that has the form 2k for some integer k. And an integer n is odd if there's an integer k, so that n is equal to 2k plus 1. Right? And I'm not going to prove it, but it would require some proof. If an integer is not even, then it must be odd. Right? That's, it may seem obvious to you, but it does take some little bit of proving. We also defined rational numbers. Rational numbers are numbers that are fractions of integers. Okay? So it can be written in the form a over b, where a is an integer and b is an integer. So if a number is not rational, we call it irrational. Okay? Now, one thing to note about this is integers are rational numbers. Right? So if I've got a number n that is an integer. Is everyone okay with this notation? I'll define it in the next section, but it's helpful if I can go ahead and use it. This means if n is in z, z is the set of all integers, so we're saying n is in z, so n is an integer. So if n is an integer, then n is equal to n over 1, which is a rational number. Okay. So integers are all rational. And so again, in terms of even and odd, I'll go ahead and make a note of that here. So we'll say that if n is not even, then n is odd. Okay? So this does need proof, but we're not going to give it here. But we'll go ahead and make it a legal theorem for us to use, a legal proposition for us to use, okay? So we'll call that a proposition. Usually I'll say prop. Okay. So there we go. So I just want to again throw that out there, pointing out that yes, it may seem obvious, but it should have some proof. Now, there are we're going to go through several different strategies for constructing mathematical proofs, okay? I'm not going to expect you to become experts in proving things. I'm never going to expect you to do more than maybe like a proof that, is like 3 sentences or so long. Okay, we'll do very simple proofs in here, okay? But I still want you to be familiar with the strategies, okay? So, the first strategy that we're going to look at is called direct proof. All right, so remember that if P is true, then this statement, P implies Q is true only when Q is true. Right? The only way that, if P is true, then the only way that P implies Q can be true is if Q is true. It's the only way that can happen. So in a direct proof, what we're going to do is we're going to assume that P is true. And then we're going to show that Q is true. That's our strategy for direct proof. Okay. So this is going to be our first proposition. So I meant to go back and number these. So let's call this proposition 1. Okay. So we'll call that proposition 1. Like it's on a ballot for us to vote on. All right. So now the first thing, we have this statement. The sum of 2 rational numbers is rational. So the first thing that we need to do with this is understand what is the conditional statement that this is communicating. How can we restate this in an equivalent as a conditional statement? If something, then something. What do we think? What assumption is getting made here? So the conclusion is that the sum is rational, right? So what do we have to assume?
If A and B are rational.
Yes.
Then A and B equals C. Is rational.
Yes, that's exactly what we want to say. So I'll use A and B. If A and B are rational, then A plus B is rational. So that's the conditional statement that we're looking for. Often with theorems and propositions that we want to prove, we'll say them in ordinary English, but we want to rephrase them in a way that says if these assumptions are true, then some conclusion is true. So the first thing that we will do is assume that P is true. So that's the first thing we're going to write. Assume A and B are rational. Now this word assume, I could say this as assume A and B are rational, suppose A and B are rational, let A and B be rational numbers. All of these mean the same thing, but we're going to state that. Okay, we're going to assert that the premise is true. So now, if A and B are rational, what does that mean? Actually, I'm going to go change these to X and Y because I want to use A and B for other things. If that's okay, I'm sorry. I should have just... You said A and B, and so I was going to roll with that, but...
I'm going to cry.
I'm sorry to break your heart over the A and B. All right, so X and Y are rational. X and Y are rational. What can we say from that? If that's all we know right now, X and Y are rational, what's the next thing that we can say about X and Y?
X equals to A over B, where A and B plus 2 the integer.
Exactly. We're going to just take the next logical step. Okay, the next simple step that we can make from this is then X is equal to A over B and Y is equal to C over D, where A, B, C, and D are integers, right? Oh, I lost my D, huh? Yeah. And D are integers. And B and D are not equal to 0, right? I think that was part of our definition. I don't think I said it when I was restating it. Okay? So now we've got this. So now what would we want to do as our next step, do we think? I've written these as A over B, C over D. What would be a reasonable next thing to do? Did you say add them?
Yeah.
Yes, let's go ahead and add them.
So you can't do that the same way with fractions. You'd have to multiply them first, which...
Right. So yeah, so I'm going to go through so at this point we can now go through the process of adding them, which will be getting part of that process will be getting a common denominator. So from there, then, so there's going to be a lot of thens, or next, or thus, or therefores, okay? So then what happens then, X plus Y is equal to A over B plus C over D, which that's equal to A over B times D over D. We want to get a common denominator plus C over D times B over B. So that's equal to AD plus CB all over BD. All right. All right, now, but what do we have here? What is AD plus CB? What kind of number is that? That's an integer, right? And it's an integer because we know that A, D, C, and B are integers. So I'll say since A, B, C, and D are integers, AD plus CB and BD are integers. All right. So I've written X plus Y as an integer over an integer. But there's one other condition, right? I've got integer over integer. Right, so we need to explain, we need to state BD is not 0. And why is BD not 0?
Because B and D,
Neither one is 0, right? So then I'll say also, since B and D, B is not equal to 0, and D is not equal to 0, BD is not equal to 0. And so now we've got all the conditions for a rational number met. So we can say now, therefore, x plus y, which is equal to AD plus CB over BD, is rational. So with a direct proof, what we're going to do, I somehow erased half of my y there also, sorry. Add that back in. All right. So with a direct proof, we start by assuming that x and y are rational, and then we're just going to take basically a sequence of logical steps until we get to the thing we're trying to prove. Does that make sense what we're looking at here? So you won't have much more complex sort of proof to do than this, okay? 3, 4, maybe 5 sentences, okay? So that's direct proof. Now, there's another proof strategy that we can use that's similar, okay? It's proof by contrapositive. Okay, so remember, this is very important. This is one of the reasons why that concept of the relationship between a conditional and contrapositive was important, right? P implies Q is equivalent. A conditional statement is equivalent to its contrapositive. So P implies Q is equivalent to not Q implies not P. So if we use a proof by contrapositive, we're going to assume that my conclusion Q is false. And then we'll show that my premise P was false. Does that make sense? Okay. So let's look at this proposition. I'll call this one proposition 2. Mostly because I'll need to refer back to it by a number in a little while. So now, let's let n be an integer. If n squared is odd, then n is odd. Now this, you could try to do a direct proof with, but it gets a little bit messy. Okay? I'd encourage you to go try to see if you can find a direct proof for this. But this will be if n is odd, so P is going to be the statement n squared is odd, then n must be odd. So if n squared is odd, then n is odd. So P implies Q. So what I'm going to actually try to prove is not Q implies not P. Okay? And I'm going to use a direct proof type strategy on the contrapositive. Okay? So let's assume n is not odd. Then what can we say about n?
It's even.
It's even. All right, now, since n is even, what can we say? What else can we say about n?
And the square must be even.
N equals
Can't
2K.
jump to that yet. That's what we're trying to prove.
N equals to 2K.
Yes.
K belongs to integer.
N is equal to 2k. Yeah, I know, you don't want us to go through, but that's, we're writing down what is the step to get us there. Yes, we have to follow the breadcrumbs. Okay? Then n is even, so n is equal to 2 times k. We can't just jump to saying n is even, so n squared is even. We need to explain why that is. Okay? So n is equal to 2k for some integer k. All right? So now that we know that n is equal to 2k, now we can look at what n squared is. All right, so now we'll say then n squared is equal to 2k squared, right? Which is equal to 2k times 2k, which is 2 times 2k squared. Okay? And this is what we're wanting to do. We want to, the reason I didn't just jump to 4k squared, well, I could have jumped to 4k squared. That would have been fine also. But we need to write n squared. If we're wanting to show that n squared is even, we need to write n squared as 2 times an integer. And so we need to show how we can do that. All right. So now we just need to explain why this is 2 times an integer. Right? So we can say since k is an integer, two times k squared is an integer. Do we agree with that? And I'm not going to make you write down, but basically, if we were really starting with a very rigorous proofs course, you would need to explain why we know that's an integer. And that's an integer because the integers are closed under addition and multiplication. If we multiply two integers together, we get an integer. If we add two integers, we get an integer. Okay? That's why all of these things have worked. Okay?
Where did we get the extra 2 from?
So if I square this, I get 2k times 2k. Right? So I kept 1, 2 here. And then I put k times 2k as 2k squared.
You can do that?
Yeah. That's just commutativity. Multiplication is commutative. So this is 2 times k, just 2k squared.
Oh,
Okay.
Sorry.
Good. I figured it was going to click in a second. Good deal. All right.
Okay. Yeah.
All right. Sweet. I was waiting for the moment. All right. Here we go. So now that's an integer. So now I've written n squared as 2 times an integer. So therefore, n squared is even. And so this completes the proof. I didn't actually do this on my last one. I should have. Often we'll put some sort of little symbol there. One that's often used is a rectangle, a bar like that. Say this is the end. I should have done that back up here too. People will often write QED at the end. It's a Latin phrase. I can't remember the Latin words, but it means something like it has been proven. Okay, something to that effect. Okay? So you'll hear a lot of mathematicians when they're in an argument, they feel like they've won, they'll say QED. So. All right. So there we go. Any questions on proof by contrapositive or direct proof? They're very similar. It just is what conditional statement am I trying to prove? Yes?
How to choose which one to use?
Well, here's what I would say. Sometimes you'll be able to look at it and see one's easier. Sometimes you'll start, and you'll have this, you'll start to try a direct proof. Okay, if I assume usually the way it happens is I start with, I have this thing that I think is true, and I know that my premise is true, and so I try to directly reason to my conclusion. If I have trouble getting there, then I will try a contrapositive. I'll see what happens if my conclusion is false.
Should we write
Yes.
the conclusion of the second proof as n squared is not odd?
Yes. Yeah, technically we should do that. So yeah, that's a good point. Technically speaking, therefore n squared is even, and therefore n squared is not odd. Yes. Based on where we are in the proof process, you are correct. I should have said that. We assume it's not odd, we assume n is not odd, and then prove that n squared is not odd. Okay. In anything kind of beyond like an introductory proofs class, we would just use not odd and even interchangeably. But you are correct. At this level that we're at, we should state it that way.
How does that prove that n squared is odd though?
Oh, I wrote, okay, so maybe I should have written,
Or sorry, I mean, how does it prove the original?
so I proved the contrapositive.
Right.
The contrapositive is equivalent to the conditional statement. That's something we showed back in section 1.1.
That seems awfully.
These
unsightly.
two are equivalent statements. Also, the other way to think about it is, okay, I assumed that the conclusion was false, and then showed that the premise could not possibly have been true. Okay? Does that make sense? So we could think of it that way also. So if the conclusion is false,
Yeah, I get
the
that,
premise.
but I don't understand how that can actually prove that.
Well, what I'm trying to say, okay, so the thing that I'm asserting is true is that if something is odd, if n squared is odd, then n must also be odd, right? So if I'm saying if p is true, then q is true.
But how does
That's
proving
one.
that if it's even, then the solution would be even prove that n, or
Well-
if it's odd, then it's odd?
Because what we just showed is that if the conclusion is false, then the premise had to have been false. So if the premise is true, the conclusion can't possibly be true. Can't possibly be false. Because if the conclusion were false, then the premise would have to be false also.
It seems like a really bad way of proving something.
No, it's actually a really amazing way of proving something. It makes for some very, very elegant proofs. Once you grasp this concept, okay? Right? I'm saying if this is odd, my assertion is that if this is true, then this is true. And it's very difficult to go directly this way. So the way I do it is to kind of come back around and say, okay, well, if this were odd, if this were false, if the conclusion were false, then the premise would necessarily have to also be false. So if the premise we know is true, if we know the premise is true, then the conclusion would have to follow. That's the only thing that can happen.
Okay.
All right. I understand this is the first time we're seeing this, and this is kind of a lot to wrap our minds around. Are there any other questions about what we did here? Do we see the process? At least. So if it's taking you a little bit of time to wrap your mind around this, basically what you can fall back on is that the contrapositive, the truth values for the contrapositive are the same as the truth values for the conditional statement. So if one is true, the other has to be true. All right, so there we go. So that's two of our proof strategies. There's a third one I want to show you. Okay? And that is what we call proof by contradiction. And so remember that P implies Q is equivalent to not P or Q. That's our implication law. So if P implies Q is true, so if the statement, if P then Q is true, then the statement P and not Q must be false. All right. If P implies Q is true, then P and not Q must be false. Right? Because if P is true, right? Then if P is true, our premise is true, and the conditional statement, if P then Q is true, right? Then we know that Q has to also be true, right? But if Q is true, then not Q is false. So P and not Q is false. Does that make sense? Does that kind of, do we kind of see what that would be?
Maybe run a truth table.
Huh? Maybe run it through what?
A truth table would actually
Well,
be helpful.
okay. So in this case, let me. I'll go ahead and show you this, but I can run it through a truth table as well. P implies Q is equivalent to not P or Q, right?
Yeah.
Okay. But this I can use the distributive law, and I can undo De Morgan's laws, and I can pull that negation out. So this is equivalent to P and not Q. But let me run it through a truth table. That might be helpful as well.
I was just
realized
gonna,
that
yeah, I was just gonna say, you just,
Yes, an and.
just distribute another negation onto it, and it would just.
I just noticed that you wrote and instead of or. That makes sense.
Right, yes. So if the conditional statement, if P then Q is true, then it cannot be the case that P is true and Q is false. That's what we're saying. Does that make sense? Right? If the statement, what's that, Josh?
I was just gonna say, is this usually when you're trying to disprove a?
No, this is a way to prove a conditional statement. What we'll do is what we're going to do is we're going to get a contradiction. We're going to say assume P is true, assume our premise is true, but the conclusion is false.
Couldn't you do it the other way around?
So you could do it, yes. So you could say, yeah. So you could use this to prove something is false, to prove a conditional statement is false. You could say that is correct. If P and Q is true, well, if P and not Q is true, then P implies Q is false. So you can do the other way around as well, which what I wrote down is really the contrapositive of my note there, right? So you can do it this way too, okay? If you have a conditional statement and you don't believe it, right, then you could assume the premise and assume the opposite of the conclusion. And show that if you assume both of those things are true, then if you can show that when you assume both of those are true, that you get something that is true. If you can show that the two of them are true, then you've shown that the conditional statement is false. So what we're doing here is we're going to use this method is called proof by contradiction. Okay? And so what we want to do is we want to show that P and not Q is false by arriving at some sort of contradiction, something that can't possibly be true, but a statement. So what we do is we reason through logical steps, and eventually we get to a statement that cannot be possibly true. It can't possibly be true. So this proof, I'm not going to expect you to repeat a proof this long, but this is one that I think everyone should see. Everyone who takes a math course should see at some point. The proof that the square root of 2 is irrational. Okay? So, our proof strategy kind of requires us to write this in a conditional form. So I'm going to write this as a conditional statement. This is proposition 4. I forgot to write this one. This is that was 2, and this is 3, sorry. So the way I'm going to write this is, if x equals the square root of 2, then x is irrational. All right. So what we'll do is we will assume the premise is true and the conclusion is false. So let's assume x is equal to the square root of 2 and x is irrational. All right. So if x is irrational, x is irrational. X is not irrational, right? So if x is not irrational, it must be rational. Okay. So we're going to assume x equals square root of 2 and that x is actually rational. So what does that tell us then about the square root of 2? If that's our assumption. We're assuming it's rational, what would be the next step?
X equals to A over B.
Yes, we use that definition of rational. That's the only step that we can make at this point. Then square root of 2 is A over B, where A and B are integers. So I'm just going to write it this way. Is everyone okay with me writing it this way? A and B are integers. And B is not equal to 0. So now, in this step, I'm going to take a step here, one step further, that would need some proof, but I will assume that A and B have no common factors. Okay, this is kind of key. I'm assuming that this fraction is in reduced form. And we can always do that, but it would require some proof to be able to assume that. So because of that, right? Because square root of 2 is equal to A over B, then A must be equal to B times the square root of 2, right? And so that tells me that A squared is equal to B times square root of 2 squared, which is 2 times B squared. So what does this tell me about A squared? A squared is equal to 2B squared. A is even. Or, yeah, A squared. Well, what we know right now is A squared is even. Yes, so let's write it this way. So first of all, B squared is an integer, so I should say since B is an integer, B squared is an integer. So A squared is even. But we just showed in that first proposition, right? That first proposition we showed by proposition 1. Since A squared is even, A must be even. Right? So we proved that. So now what's our next baby step? A is even, so what does that tell us?
B is even.
That's where we're trying to get to, but it takes a little bit more work. We can't jump to that yet. A is even, what does this tell me? If A is even, what has to be true? Next baby step. Just use a definition. What's the definition of even?
A equals 2 close to?
Yes, or
Sorry,
2 times k.
2 times k.
Yes. So A equals 2k for some integer k. All right, so now A is equal to 2k. So now let me go back here. What that means is that 2k, so A was equal to, on one hand it's equal to 2k. On the other hand, let me write it this way. So A, which on one hand is 2k, is also equal to 2 times the square root of 2. Right? Did I say 2? Oh, sorry, not 2 square root of 2. A is B times the square root of 2. Right? So now what happens? All right, I'll change that to then, just so I don't use the word so. So then A is 2k equals B squared. So that tells me that A squared is equal to, on one hand, it's 2k squared. And on the other hand, it is B times square root of 2. All right. So I'll use thus, okay? So because of that, we know that 4k squared must be equal to 2b squared, right? Right? Yeah, yes.
Wouldn't that be b times the square root of 2 squared?
Right. Square root of 2 squared. Oh, yeah, there should. I didn't write my squared there. Yes. There should be a squared here. Sorry. I wrote the parentheses and forgot to write the square. We're squaring all of that. So A is equal to 2k, which is equal, and is equal to B times the square root of 2. I square. Squaring one of these means I'm squaring all of them. So 2k squared is equal to B square root of 2 squared. Yes, Josh?
These are going to be on our quizzes. We're going to need a little longer for our quizzes.
Yeah, this one is not. This one is not. This one is longer than what we typically do, but I want you to see the process. Okay? So 4k squared is 2b squared. I'll divide through by 2, so 2k squared is equal to b squared. Aha. So what does that tell me?
B squared is even.
Yes. So I'll even make this statement, since k is an integer, k squared is an integer, so b squared is even. So now, by that proposition, that first proposition we proved, go back to prop 1 again. By proposition 1, what does that tell me about b? B is even. Yes. So b is equal to 2 times h for some integer h. But now, right, as Flair just said, a and b have a common factor. So we've reached our contradiction, but now A and B have a common factor of 2. So this is a contradiction, right? Because we assumed they didn't have one. This statement can't possibly be false, that A and B have a common factor. Okay? So therefore, x equals the square root of 2 is irrational. Okay. So again, I'm not going to ask you to walk through this sort of proof. I'm not even going to ask you to walk through one quite this complicated on your own. Okay? We just don't have the time. If you're pursuing, like if you want to add a math minor or double major, or if you're CSMA, you'll go through a course called Logic Sets and Proofs, where you'll go through all of this much more slowly, okay? And learn how to do this. And learn how to discover some really, really, really interesting things in math. Okay? But this is kind of the basis, and this at this point is still kind of complex. But this is one proof that I think every student needs to see at some point, if they're in a mathematically related field. Yes, what?
Should all of the proposition 1 in this proof to proposition 2?
Should what?
So all the proposition 1 in this proof.
Oh, is it proposition 2?
Yeah, I think it is.
Oh, that is proposition 2. You're right. Proposition 1 was the rational one. So yeah, let me change that. Thank you. These should be proposition 2, not proposition 1. I didn't look back through there properly. So yeah, those two statements, it was proposition 2 that we were using, not proposition 1. All right. So that's proof by contradiction. And there's another, I was going to talk about equivalences, but I think in the interest of time, I'd like to go ahead and get started on the next section. And so we'll stop here, okay? But the general strategy with the proof by the big thing to take away from this right now, and there will be a couple like this in the homework. There will be homework over this. Is that you assume the premise is true, which in this case is that the premise is, square root of 2 is some number. We just call it x. Assume the premise is true and the conclusion is false, and arrive at a contradiction. Okay? So, if the premise is true, the conclusion can't possibly be false. All right, does that make sense? So this is the same sort of thing that you were saying. All right? So let's stop there with logic, and I want to shift gears. All right, that wraps up our discussion on formal logic. And now I want to move over to section 2.1. And we're going to look at a branch of math called set theory that is strongly related, closely related to logic. Actually, a lot of the basics, the foundations of set theory are kind of go in sort of like a one-to-one correspondence with formal logic. In fact, depending on what textbook you're looking at, sometimes you start with set theory and then use that to motivate formal logic. Our textbook, our class uses formal logic and then uses that to motivate set theory. So I'm talking about set theory. Well, we should probably say, what is a set? So a set, it's editable. So a set is just going to be an unordered collection of distinct objects. An unordered collection of distinct objects. So, they're unordered and distinct. So it doesn't matter we're not thinking of these objects in any specific order, right? Like I've got, right in front of me, I've got a phone, a water bottle, and a notebook, right? That'd be a collection of just 3 distinct objects, okay? And I don't have them in any order. I could talk about that group of things as the phone, the water bottle, and the notebook, or the notebook, the water bottle, and the phone. Doesn't matter what order I say them in. They're all the same set. Okay? So the objects of these sets are called elements. Okay? And so if I have a set A, and I want to express that X is an element of a set A, we're going to write this notation that I was already kind of using, but this is formally what it means. It means that X is an element of the set A. Typically, we're going to read this as X in A or X is in A. Right, depending on the context we use it in. Like if we use it with a conditional statement, we might say if X is in A, then blah 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 blah. But we also might write for all X in A, for every element X in the set A, we might just say for every X in A. So, but we would use the same notation. Okay? Now, if we have two sets, we want some way to compare them. And we'll say that two sets are equal if and only if they have the same elements. Okay. All right. So these are kind of the basic ideas of what a set is. Okay, a set is a collection of unordered objects, unordered collection of distinct objects. We call those objects elements. Two sets are going to be equal if they have the exact same elements. So maybe we want to be able to actually write down a set. So I had this collection, my water bottle, my phone, and my notebook, right? I could write that as a set. Now use the basic way of writing a set is called roster notation. And so we're going to use curly braces that look like this on each side. So I had my water bottle, phone, and notebook. So, notation matters, guys. Notation matters, all right? Okay, actually, well, I'll get to that in just a second when I've got something a little less that I can write the sets, okay? So, we could do this. We could say there's a set A, B, C. What's that?
I was just going to ask, how would you notate the set of all sets?
There is no set of all sets.
There isn't set theory.
No. It's actually not well defined.
Oh, really?
Yep.
Oh.
Because you had a set of all sets, and that set would then necessarily have to be inside of that set, and then it would make that a bigger set.
Yeah.
So it's so the statement there is a set of all sets is it's the statement that if it was true, then it would have to be false.
Well, okay. Then there would have to be.
Well, actually, yeah.
So if a set of all sets is a thing that would be a contradiction. A set of all sets that do not contain itself
But
would
okay.
exist.
Set of all sets that do not contain itself. Okay. Yeah.
How would you notate that?
Well, we'll talk about some ways to build some sets. I would need to think about that particular set that you're talking about. We're going to build up to where you could define something like that. Okay? But we could just say, let this be the set of all sets. The set of all sets that do not contain itself. Something like that. Is there a question? Yes, on?
Can you give an example of not distinct or non-distinct objects?
Yes, I'm going to get to that. So, let's say that I had a set like this. A, B, A, C, C, B, 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 A, C. Okay. Well, this is the same thing as A, B, C. Doesn't matter how many times I wrote down the A. The A is in there. Yes, so when I give you a Python assignment like this, they have a set object. And so if I try to add, if it only has the character A in it, and I try to add the character A to it, it just doesn't change the set. Okay, since it's already there. Okay? All right, and this, it's unordered. So this is the same thing as saying CBA. All right, these are the same thing. Now, very important, notation matters. These curly braces are what are indicating that this is a set. Okay? This is not the same thing as A, B, C. This is ordered. All right. Standard mathematical notation, anyone who studies math would look at this and say a set. They would look at this and see an ordered triple. Unless you had somewhere, if you're writing a paper, unless you somewhere stated that this was a set. Okay? This notation would be confusing to anyone reading that. They would think this is an ordered triple. Okay? And this is not the same thing as just writing down A, B, C. Okay? This is a sequence of numbers or some list, I don't know. Right? So my point is notation matters. Make sure you're using the right notation. All right. Now, with this roster notation, we could have an infinite set. And we could have a set like 0, 1, 2, 3. And we're going to continue in that manner. So we usually use 3 dots. The ellipsis is the proper English term for it, to mean continue in this pattern. Okay? We could write 2, 4, 6, 8, ... So this would be, so this first set, 0, 1, 2, 3, on to infinity. This actually has a special name and notation. We'll call these the natural numbers. Okay.
How do you write those fancy letters?
Okay. Practice. Okay. So I'll write them down. So
I just think it right.
that's okay. So the N for natural numbers, I always write 2 vertical bars together, and then I draw from the top of one to just above the bottom of the other, and then just below the top of the left one to the bottom of the right one. That's how I'll make the N. For my Z, I'll actually draw a 7. And then I'll draw kind of an upside down 7. That way. And yeah, I guess at some point I just decided that's how I was going to draw those. So yeah.
I'm trying to replicate it. It might just do not look good.
Yeah, it's okay. It's okay. For the real numbers, I will draw 2 bars and then draw the R around it like that.
Okay.
Okay. So that's how I will do those. And then I'll go ahead and say it. The rational numbers we've already seen. So I'll just draw the Q and put the bar in it. And so those, and complex numbers, I'll go ahead and say C is the complex numbers. I'll do the same thing. So these are kind of the ones. And yeah. It'll just take some practice for you to figure out how you want to write them.
It's like learning how to write a Japanese character. You gotta take the right steps.
Yeah, you gotta, yeah. Well, I mean, writing an English letter, right? At some point you had to learn the right steps to write the A, right? That's why you have, for little kids, you have all these books that have like little arrows, like trace this way, you know?
Japanese is especially precise though.
Yeah. Yeah, I haven't studied Japanese, but it is quite difficult. Characters are complex, and so.
Chinese will be more complex.
Do what? Chinese.
Chinese characters will be more complex.
Yeah,
Well,
that's what
they
I'm
don't
saying.
have like hiragana and katakana.
All right.
characters.
Okay, so all right, so we're done. We'll save this. We'll table this this debate for after class. So, but anyway, that's how I do that. Okay, so the dot 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 just means continuing whatever the pattern is. Okay, so this would be all even numbers, all positive even numbers.
Or wouldn't it be just all even natural numbers?
No, because 0 is even. 0 is 2 times 0.
Oh.
Yeah.
Well, you could then write it
Not equal.
all,
Except zero.
like you could make an exception, couldn't you?
Yeah, yeah, you can.
So you can say all natural even numbers.
All even natural numbers except 0. Yeah, but we may as well just say all positive even numbers.
Then you don't get the part fancy limit.
I should probably say integers. But I guess even implies that you're working with integers. Okay, so again, just let me go ahead and say order. So looking here, order and repetition do not matter. It doesn't matter what order you write them in. It doesn't matter if you repeat the elements. You get the same set. So, if I wanted to ask what's the set of all vowels in the English alphabet, I would write down A, E, I, O, U. And I'm not going to put Y because I can't determine if it should be in there or not. Sometimes it's a vowel, sometimes it's a consonant, so it's its own special letter.
I think it's a consonant. It serves as a substitute vowel.
Okay. I'm not a linguist. I haven't really thought that carefully about how we classify them all. I just know that functionally, when I see a Y, it either functions as a vowel, or sometimes it functions as a vowel, sometimes it functions as a consonant.
Mm-hmm.
And so, yeah, I think maybe people who really study this might throw it into consonants with whatever the qualification was. It serves as a substitute for an I or something like that. But yeah. Yes, Josh?
Can you put prepositions in sets?
Can you put what?
Prepositions in sets?
I don't quite understand.
Like,
you could have
a set of prepositions so that, P implies Q equals true, or
propositions,
a different
yes.
preposition. Oh, proposition.
Yeah. Okay. So that. Okay.
Sorry.
Yeah. Yeah. You could. You could write. Yeah. A set of propositions. You could have that. You could have that. Those will be objects.
So,
And yeah.
including the truth value, like equals true, right?
Yeah.
Would that work, being that because it's an equivalency, even though they're different
Yeah.
propositions,
So-
the truth values may.
So we could think of it. We could think of that as pairs. We're going to look at something very similar to what you're talking about. We think of this as pairs of proposition truth value pairs.
Okay.
And yeah, we can totally do that. Okay. So, or let's say the set of all positive odd integers less than 10, right? So 1, 3, 5, 7, 9. Okay? Now, what have I done here in these examples? Right? I've taken some sort of description and then I have written it in some sort of set notation. But I've defined it here with a description. And often, it's very handy to write, have a way to write down a set using some sort of description or some sort of constraints on the elements in that set. And we call that set builder notation. Give me a second here. Okay. So let's say this set 1 here, right? The set of all vowels in the English language. Okay, so I could write that in set builder notation like this. I could say the set of all X such that X is a vowel. And I'm going to say vowel in the English alphabet, okay? Yeah, I guess we'll say that.
And this is kind of like declaring your domain in a.
Yeah, exactly. So the domain, yeah, that'd be a way of thinking about it. A domain for a proposition, or for a domain for a predicate, is a set. It's the set of all values that you can put into it. Okay? So, but the basic way we do this is, okay, we've got a variable. We've got this bar that's always read such that. And then over here we have a description. So let's say I had this set right here. The set 1, 4, 9, 16, 25, and so forth. Okay? Now, the problem, so what is happening here? So what is this set? How would you describe this set? Yeah, the set of perfect squares of integer, right? Perfect squares of an integer, yes. The set of all perfect squares. But you had to make some sort of inference to get there, right? We had to look at this and say, okay, well, you've written down 5 terms in a sequence. It looks like you are squaring each time, so I'm going to infer that this is all the perfect squares. Okay? But that could be problematic, right? Maybe you have some sequence that you start your set builder with, your roster notation with, and then you see it as one pattern, but then someone else comes and sees another pattern in it, right? So that's not necessarily always a great way to write this down. So let's write this down formally using set builder notation. So this is going to be the set of all n such that n is a perfect square, like Flair said. Okay. Now, this is perfectly fine way to write this down, but mathematicians, we often like to write things down a little more concisely. So we don't always have to have a variable here. We can put some expression, okay, and then describe some things about that expression. So I could say this is the set of all n squared such that n is an integer. So I can write n is in z. So this would be a perfectly valid way to write this in set builder notation.
Should that be natural number because 0 is not inside?
Ah. Okay, yeah. Okay, so what I'll write, we'll get to these in a second. I'm going to say z plus. Z, if I put a plus with that, I mean positive integers. Thank you. Yeah, I should have had the 0 over there. But this, the point with this is that we can use not just a variable, we could use an expression. Okay? So that's where we'll stop for today. Are there any questions about any of the set theory stuff? Was that your note or yeah? All right. Good deal. Well, that's where we'll stop for today. Thank you guys very much. Have a good day. I'll see you all on Tuesday.